So the first thing to point out is like schedule based. So here's us right here. We're going to be talking about the law of cosines today. We'll get to that in a minute. There's some extra credit posted, all that standby. This will be the only day we meet this week because of fall break. One thing that is posted right there is there are some like practice problems already posted for the midterm that is the Friday after Thanksgiving break. So the Friday of next week. And you also now have all of the material needed for that midterm. So if you want to start prepping those problems, go for it. What are the topics we'll cover? Well, I've even sorted this according to topic. We'll do some trig identity stuff. We'll do some things with inverse trigonometry. We'll talk about solving trigonometric equations some. And then we'll do a few things with the area formula, law of sines, law of cosines we've been hitting the past couple days. So, you'll notice that this document is 42 problems long, but it's really more than 42 problems long because, like, part 8 has F many parts. Part 7 has I many parts. So it's like a ton of problems. It's way longer than the actual exam will be. Like, you know the length that I like calculating exams now. But go through these. If you're prepped for these problems, you'll be prepped for the exam. Gesundheit. There's also a review posted in Canvas, right? Did I actually post it? Okay, cool. And that has the usual rules. You get, I think, 3 submissions. It'll tell you which problems you got right or wrong. So, like, you can't just brute force the multiple choices, but think about what things you're struggling on. Shoot me some email questions. And there's the usual incentive. If you catch any errors in these documents, you'll get some bonus points. If it's like something stupid and grammatical, then like I'll give you something for your time, but it'll probably be less than a full bonus point. Groovy. So after that midterm, I'll do my best to get that graded even like by midday the Saturday after. So like those grades should get posted real quick. And then as soon as I do that, I'm going to post a Canvas item in which I will ask you to tell me which exam you want to redo. And then on that very last Friday, that very last day that we meet, I will have a mulligan attempt. You'll be able to get full points back on an exam. One. You'll tell me which one. After that, there will be a day during finals week when we will meet to review for the final, and then on December 17th, Gesundheit, which is the Tuesday, I believe, right? I think. So probably the Monday I'll post a review time. And I'll make sure that it overlaps with the noon hour because I know that no final exams are scheduled for noon. So if you've got like an exam that ends at 11 and one that starts at 1 p.m., then like, you know, maybe you don't want to come anyway because you need to eat lunch at some point. But otherwise, you definitely have that hour to come talk. Cool. We feeling good? All right. What I might even do is try to resolve a room. Cool. Let's start it on what I want to talk about today. So I'd like to talk about today is the law of cosines. And the law of cosines, you should think of it as being like the Pythagorean identity, but when a triangle is not a right triangle. So I think I want both things open. So I'm going to start up at the top. Here is a right triangle. So if you happen to know that this is 90 degrees, and let's use the same as in the Desmos, 6 and 4. There's a side length of 6 and a side length of 4. It's a hypotenuse, so let's call it H. No, let's call it C. Make it match the picture below. Is it possible to determine the side length C in that triangle? What equation would you use? Yeah, Pythagorean theorem. Side squared plus side squared equals hypotenuse squared. And then you could solve for c. Let's see what if you were in a situation that's not so pleasant as this? What if that 90-degree angle wasn't actually a 90-degree angle, or actually like a 71-degree angle? Would that equation still hold? No, that hypotenuse length would get shorter if the angle became smaller. And I have a little like Desmos demo pulled up. So if I change that angle instead to be, let's do it exactly, 72. Oh, notice this side length is shorter than it used to be. If the side length grows, then that length gets bigger. So we want there's probably some formula that models that though, right? If you know two sides and the angle at which they meet, you can literally just take two side lengths, have them meet at that angle, and draw the straight line between them and measure that distance. So you could know that distance. There should be a formula. And trigonometry does give you such a formula, and here it is. The law of cosine says if you have edges A, B, and C of a triangle, and theta is the angle opposite C, so I am going to emphasize that. Theta is the angle opposite the side length C, then C squared is equal to A squared plus B squared minus. So with just A squared plus B squared, that looks like the Pythagorean identity. So the next thing I'm going to write should measure like how far that angle is from being a right angle. And here's what you wind up getting. You need to subtract 2AB cosine theta. And let's just think about why that's sensible. If that angle theta becomes obtuse, then cosine is negative. So then you subtract a negative, you make c squared a little bit bigger. Oh, and that's what you expect. If you're opposite obtuse angle, then you should be a very long side. And this agrees with that. Cool. That formula look okay? Let's use it to do some stuff. That's what we're going to do today. I will emphasize one thing, because this is a thing if you don't think hard enough about the problem, you will make a mistake in. Those two need to be opposite each other in a triangle. This theta and that c need to be opposite each other in that triangle. So let's use this to do something. So there's a triangle. You have a side length of 5 and a side length of 3. They meet at an angle of pi over 30. Is that enough information to determine the side length c? Yeah, I think so. And maybe I'll give you options. I do it, or I be quiet for a bit, and you do it. You want me to do? Cool. Then I will be quiet for a bit. Simplify it exactly and approximate answer, and we'll also do what I want. And once you have an answer, exact or approximate, I guess. If you don't have a calculator, you can't get the approximate answer. Tell me what answer you're settling on. Well, and also check with those already. Make sure you have something consistent with your AORs. If you do, then you probably don't know. see lots of promising answers. Let's hear it. Exact value is? Yeah. I go root 19. And in going through, I saw a particular error, which is a really common error that I see on exams. And whenever I see it on an exam, it makes me really sad on the exam. So I'm going to quickly go through some sample walk on this one. You'll tell me where I went wrong. And we'll see if this is even the same mistake I saw other people. It might have been. It's hard to diagnose an error at like a glance. So let's start by just writing down what the law of cosine says. Law of cosine says that c squared equals 5 squared plus 3 squared minus 2 times 5 times 3 times cosine of pi over 3. All right, that down correctly? That's not where I intended to make a mistake, but you know my ability to write things down correctly. So let's see what we can do from there. So let's see, that's going to give me c squared equals 5 squared is 25 plus 3 squared is 9 minus, 2 times 5 is 10 times 3 is 30 times cosine of pi over 3. So far so good? All right, so next, let's see, 25 plus 9 is 34. Minus 30 is 4 cosine pi over 3. Any objections there?
The 30 is multiplied with the cosine, so 34.
Yeah, there's an order of operations issue. Multiplication is resolved before subtraction. So the 30 is multiplied by something. I can't do the subtraction like that. So how many people had that error in their walk? Cool. Better to make the error now than a time that matters. All right. So still 25 plus 9 is 34 minus, what's the cosine of pi over 3? It's a half, right? So it's really 34 minus 15, yeah, that's 19. C squared is 19, C is the square root of 19, and I've already forgotten the decimal approximation. Feel good? Nice. So, there are some pitfalls to avoid when using the law of sines. Keep in mind the precise statement of order of operations. But if you do that, at least that possible downfall will happen. There's another one when you use it for a different rule that might happen. But we'll talk about that momentarily. All right, so before moving on, one of the things that I've been trying to push in the discussion of law of sines is a triangle has 3 obvious numbers associated. 3 sides, 3 angles. But really, if you know any, in general, any 3 facts about a triangle, you know that triangle. The exception is if you know all 3 angles, you don't really know the triangle, do you? All right, if you have a 45, 45, 90 triangle, that doesn't tell you what any of the sides means. It could be 1, 1 and the square root of 2, or it could be, I don't know, all those numbers but all multiplied by 7. So, in the case you know all 3 angles, you don't have enough information, that's fine. It turns out in the hyperbolic setting, if you know all the angles in the triangle, you do know what the triangle is. But we don't do hyperbolic geometry in this class. If you want to look into that some more, let's see, there's a class called Foundations in Geometry. I think that's the name of it. That's an interesting class to take. You'll do some hyperbolic geometry. If you know 2 angles and a side of a triangle, then we have an approach. You can find the unknown angle, since angles add up to 180 degrees, or pi radians. And then you definitely know a pair consisting of a side and an angle opposite, so you're set up to use the law of sines. if you have a side angle triangle, so what do I mean by that? You're in a situation where you have a triangle, you know a side, and you know an angle. Then we have an approach to find everything about that triangle. We're set up to use the law of sines, right? You can set yourself up to use the law of sines to find sine of this angle. You can then use inverse sines to figure out what that angle is, except there's this weird subtlety. If it's possible that that angle is obtuse, inverse sine won't tell you. So you need to do some stuff to figure out whether or not that angle might be obtuse, and then go from there. So far, so good? Nice. And once you know that angle, you can figure out the remaining angle, because the angles add up to 180 degrees, and then find the missing side. If you have a side angle side triangle, like this one, side angle side, well, then we've already seen what to do. Use the law of cosines, not inverse trig yet, to find the missing side length. Oh, cool. Now you know all 3 sides in the triangle and you just have 2 missing angles. And let's maybe even just talk about this. So let's continue this example right here. So you know that this is a 5, that's a 3. Here's a root 19. This angle is pi over 3. If I asked you to find the remaining missing angles, what would you want to do? Are we set up to use the law of sines? Yeah, we know a pair consisting of an angle and a side opposite. So let's do that. Sine pi over 3 over root 19 equals, I guess we should give these names, A and B. Which would you rather try to find first, A or B? And there is, in fact, a wrong answer here. How many people's intuition would be, let's find A first? Cool. An objective reason, or just because it's a false alphabetical? Okay.
You don't have to find obtuse angle?
There you go. That angle B, that angle A, is it opposite the longest side length? No, so it can't be obtuse. So that means we don't have to deal with this weird, like, oh, it might be obtuse, because we just know it's not. Sine A over 3. Do some walk again, what A equals. All right, now that you know A, how do you find the remaining angle B? Yeah, and in this case, pi minus, because they're in radians, not degrees. Yeah, so pi minus pi over 3 minus whatever it is, which we haven't found in that one. So, in general, you can use the law of cosines to find the missing side. Next, you can use the law of sines. You could also have used the law of cosines to find the missing angle, and we'll do that on the next page, in fact. And if you use the law of sines, find the one that might be obtuse last. Because the one that might be obtuse is the one that has this weird ambiguity, but only one can be obtuse, and you know which one. In this case, the angle that was opposite 5 might be obtuse. Cool. We feeling pretty good? Alrighty. So, the last case is a side triangle, and let's just take a look at it. I should write the law of cosines on the board. So let's just think algebraically about what is what is practical to solve for in the law of cosines. If you wanted to know C, is C basically already solved for? Yeah, you need to take the square root of both sides, but that's fine. If you wanted to solve for A, would that be doable? doable. It'd be annoying because there are like two instances of the variable a, right? So you have to set yourself up to use like the quadratic formula. So not a great idea. Don't use it. Don't use this to find the side lengths a and b. You should use the law of sines if you need to find those. If you need to define the angle theta, how many thetas appear in this formula? Just one. So it's practical to use this to find theta. Let's do that on the next page. So if you have a side-side-side triangle, like this one, you can determine this triangle. You can determine all of the angles if you know all of the sides. And like, that's not a surprising fact, right? If I give you like 3 planks of wood of lengths that you know, there's only one way to put those 3 planks of wood together into a triangle. So this formula has to exist. It's just a matter of how complicated could it be. And the answer is not terribly. So here's how I think I want to do this. We will find one of those angles altogether, and then I'll break you all up into subsets, and you will find the remaining angles in those subsets. So I think I'm going to start even at the bottom of the page. Let's find the cosine of gamma. And the reason I'm doing that is because this picture is drawn as if theta is in the bottom left corner. It doesn't need to be. You can put it in any corner you want. You'll just get a different looking formula. The thing you need to keep track of is those two need to be opposite. So let's write down the law of cosines centered at this angle gamma. So let's see, law of cosine says the square of the side length opposite gamma equals the sum of the squares of the remaining 2 side lengths minus 2 times the product of those 2 side lengths times cosine. So let's write down that equation here. Gesundheit. So gamma is opposite 3. So 3 squared equals 6 squared plus 4 squared minus 2 times 6 times 4 times the cosine of gamma. And while writing that, I felt my mind just get a little bit wobbly. So, did I just write anything stupid down there? Did it look okay? All right, so that's an upshot of like having people who are inspecting your work while you do it. Having people regularly do like the homework and stuff for this class with other people collaboratively. And that's like really helpful just to have someone else who's looking at your work while you're doing it, right? Or even if you're both just doing the same thing. All right, so let's carry on. I need to solve this for gamma. Let's start by solving for cosine of gamma, and then we'll talk about any weirdness that can happen with the inverse trig stuff. So let's see. 9 equals 36 minus 16 minus, nope, that's a plus. Gosh, 2 times 6 is 12 times 4 is 48. Cosine gamma. I don't want to get cosine gamma on its own, so I guess start with cosine gamma, multiply by minus 48, then add these to it. So I guess subtract these to the other side. So far sensible? All right. 9 minus, gosh, 6 plus 6 is 12, carry the 1, 52. Gosh, 52 minus 9 is 43, but it's negative. So negative 43 over negative 48 equals cosine of gamma. Let's lose those negatives. Cool. So that's like a lot of negative signs that appear in that computation. So how many people in here just feel like keeping track of negative signs is a weakness of theirs and they're liable to make a mistake of that sort of thing? Cool. That's just a good thing to be aware of on your own. once you finish a lot of cosines computations, see if you've screwed up any negative signs. Just like go through and see if things have been subtracted correctly, see if you've divided by a negative. All right, so we have now gotten to the point where cosine gamma equals 43 over 48. And you know like what you want to do. You want to take inverse cosine, right? That should undo it. And let's think if there's anything silly that can happen because inverse cosine doesn't really undo cosine. Trust. What's the range of inverse cosine? Draw in your head the graph of cosine. How many angles can you include while still having it be 1-to-1? Or draw it on paper.
Negative pi over 2 pi over 2.
Nope. That's not 0 to pi. All right, the graph of cosine looks like that. So how much of it can I include while still being 1-to-1? Well, I can make it up to that valley. Oh, sorry. So there's the graph of cosine. If you start at 0 and go forward, you can make it to that valley while still being 1-to-1. And that is 0. That valley happens at pi over 2. Nope, pi. So the range of cosine inverse is 0 to pi. So in degrees, that's the same as 0 to 180 degrees. What angles are allowed to theorize a triangle? Angles between 0 and 180 degrees? So the angle output by inverse cosine is the same range as angles allowable in a triangle. So that means there's not this weirdness that it doesn't see the obtuse choices. It will. So there's no weirdness like with the law of sines. You just get to know that gamma has to be cosine inverse of 43 over 48. Because you already know gamma is the option which is in between 0 and 180 degrees. And I guess now decimal approximations. I think I'd like to get an answer in both degrees and in radians, for the sake of having both. To get the answer in radians, I have a tool that I don't know how to put into degree mode, so I'll find it in radians. Arc cosine of 43 over 48. 0.46 radians. In degrees, multiplied by 180, divide by pi, because that's how you change radians to degrees. 26. And I think I'm going to round my degrees out to the nearest whole number because we'll see something goofy happening at the bottom that I want to see. 26 degrees. People feel pretty good? So what do you think? If you wanted to find one of the remaining two angles, could you follow basically the same steps? So here's what I'll have you do. I'm going to break you all up into subsets to determine the remaining angles. Alpha, beta. And you know, for the sake of like not having the confusion come from what are the Greek letter names, section if you want to do. Cool, we get it. Looks good. Here's the previous section. Yeah. I didn't check your one, but go ahead, sorry, please. Yeah, so keep the 16 on the other side of the side. Add those two together and see what she does. Cool. Yeah, that'll give me the budget. I have written down plenty anyway. Yeah, cool. I only have it written down to the ones that they that
Oh, I did it.
you have the digits of body body. Cool. How are we feeling? So, let's come together a little bit. So, I think I want to jump right to the stuff we did in like the last column on the bottom one. So, after solving for cosine of alpha, what fraction did we wind up with? You know, 29 over 46? Did you get settled down on that eventually? All right. Yeah, I suspect it was just like some silly arithmetic thing. Is there a call to go through the walk to get cosine on its own? Cool. 29 over 36. Oh yeah, 27 over 36 wouldn't even have been simplified. So apparently then alpha itself should be inverse cosine of 29 over 36. And that's not like a number you see on your units awful. So you can't like tell me on the nose what that is, but if you have a calculator you can get some approximations. What is that about? Radians are degrees. 36.34 degrees. I'm going to round everything off to the whole number of degrees. Like there's no directions that say that's what I want, but something particularly interesting will happen at the bottom of the page if I do that. Radians.
0.63.
Groovy. All right, let's do the other one. So you solve for cosine of beta. What number do you wind up getting? Cool. Do I hear a second? Nice. So here's the thing that I want to point out. This is negative. Cosine is allowed to be negative. But let's think about when it's negative. So in quadrant 1 it's positive. In quadrant 2 it's negative. Well, that's a pretty big angle my arms are making. That's like an obtuse angle. A negative value for cosine corresponds to an obtuse angle. So as soon as you see a negative here, that tells you that that angle is bigger than 90 degrees. It's obtuse. Which means If you had tried to find beta using inverse sine instead of inverse cosine, you wouldn't have been able to. You would have gotten two different options because sine doesn't know if it's positive or negative. You would have gotten like two different options, but one of them is illegal. All right, so cosine of beta is that. So I guess beta has to be cosine inverse of that. I know that that's bigger than 90 degrees, or pi over 2 radians. Let's get those decimal approximations, though. What is that about? 2.046. So I guess I would round that to 2.05 just to stay consistent with how many digits. How many degrees? 117 degrees with some change, but it rounds off to 117. All right. So I want to do one last thing just to double check, because it's worth knowing that you can always check your answers. What's something easy you could do to check if these answers are reasonable? Yeah.
Add it to 180.
Better add up to 180 degrees or pi radians, but I think in this case it's easier to recognize 180 degrees than it is to recognize pi radians. So let's add these up and see what we get. So to check, alpha 36 degrees plus beta 117 degrees plus gamma 26 degrees. They add up to, yeah, I hear 179 degrees. And maybe just a show of hands. How many people, if they were doing that check, would just plug it into a calculator instead of doing it by hand? Yeah, fair enough. It's like at the edge of what's quicker to do by hand. It's 3 two-digit numbers. 179 degrees. Wait, that's not equal to 180 degrees. Does that mean something went wrong? Why not? Yeah, there's just some rounding errors that are built up. You rounded off alpha to the ones place, you rounded off beta to the ones place, and gamma to the ones place. That means for each one of those, you have like a plus or minus a half margin of error. Well, if you add up 3 plus or minus a half,